Hello and welcome to Carl & Cymru e-sgol sessions. Today we're going to be looking at AS Unit 2, the conduction of electricity, and as a special treat we're going to try and do resistance as well. These are two relatively small topics, or at least the first one is, and we're going to try and get through these two topics in this 45 minutes. Now, my name is Mr. Ridd. I'm sure you probably know who I am by now. I sounded really big-headed, didn't I? Well, if you've watched some of these videos, I've done a few. That's what I really meant to say. As well, on the point of other videos, please check out the Carl & Cymru website, where you can look at previous recordings on a whole range of AS, A2 and GCSE content. So, recommend it to your friends. Check it out. A really good resource to use. Let's get into it then. So we're going to start off by looking at the conduction of electricity, the first topic in Unit 2. And here, as always, I've got the specification. So to begin with then, with electricity, we have to really think about what it is. And essentially, it is the movement of charge. Just in the same way that a river is like the movement of water, electricity you can think of as the movement of charge. Now, what is charge? That's a tricky question, and there aren't many great answers for that. Charge is a property that protons and electrons have, and it comes in two flavors, positive and negative, as I'm sure you're already aware. But beyond that, there's not much to say other than it exerts and is a part of electromagnetism and electrostatic forces. And it's this property of electrostatic force that really underpins electricity as we know it. And you can think of electricity as how we have manipulated electrostatic forces, bent them to our will in order to make something useful out of them. So the unit of charge is known as the coulomb. We've got that written up here. The unit of charge is known as the coulomb, capital C. And then an electron charge E is a very small fraction of a coulomb. Right. So let's think about what that means for a second. Well, 1 coulomb of charge is actually going to be comprised of lots of fundamental charges. Now, you should all be aware by now that electrons and protons have something which we refer to as the fundamental charge. It's the smallest charge, it's the smallest unit of charge. You can't get any smaller. And that number, E, as we sometimes refer to it as, okay, the fundamental charge, is 1.6 times 10 to the minus 19 coulombs. In other words, a very, very, very small amount of charge. Now, protons and electrons both have this same fundamental charge. In the case of protons, it's positive. In the case of electrons, it's negative. It only comes in two flavors, if you like. One of the great mysteries in physics, though, is as to why it should be the case that the protons charge and the electrons charge, one being hadron, one being a lepton, why should they both be exactly the same yet opposite? And that's one of the fantastic mysteries that we have. There's nothing in physics that says they should be exactly the same, but they are. Could be a happy coincidence. Who knows? Who knows? Anyway, so 1 coulomb charge then is comprised of obviously a lot of charge carriers, and we can actually work that out. So how many electrons are in 1 coulomb? Well, if we just do 1 divided by 1.6 times 10 to the minus 19, then we're going to end up with, well, a rather big number. It's 1.67 times 10 to the 18, I think it is. Yeah, 18 electrons. Okay, or protons if it was positive, okay, but that's how much is in 1 coulomb. It's a big, big number. It's a hard number to wrap our heads around. So that's all we say with the first part. I'm going to go ahead and just give that a little tick, I think. For some reason my highlight has gone enormous. Let's take that down a notch. Try again. Okay. Fact, the charge can flow through certain materials called conductors. To be honest, there's not much more to say about that. You'll already be aware that we categorize materials as to whether they're conductors and insulators, and conductors can transfer charge, they can carry charge effectively, they can carry a current, they conduct electricity, and insulators do not. Now, as to why that is the case, well, it all comes down to fundamentally how many charge carriers are available, how many free electrons are there to transport or to carry a current. And in the case of insulators, the answer is not that many. Now, electrical current, we'll go on to part C here, is described as the rate of flow of charge. Now, whenever we see the word rate, what we mean is per unit time. Okay, so it could be anything. I mean, you know, the rate at which I can eat muffins, right, might be measured in muffins per minute. Yeah, you can eat 3 muffins per minute. Could I eat 3 muffins in a minute? No, probably not. Anyway, the point I'm making is it's per minute, it's per unit time. So whenever we see rate, we mean per unit time. So electrical current is the rate of flow of charge, which leads us on then, of course, nicely to this equation. I is equal to the change in charge, or the amount of charge per unit time, or in this case, delta Q over delta T. Remember, delta simply refers to change. So there we go. We've got that equation. We've explained it. You need to know, what current is as a definition. That's given in part C there, and you need to be able to use the equation, which we will do a little later on. Now, part E, current being measured in amperes, A, where 1 ampere is, if you like, a coulomb per second. I mean, that's just derived directly from there, isn't it? All right, and because I is equal to Q over T, charge is obviously measured in coulombs, like we just mentioned. Time is measured in seconds. So remember, when we've got seconds on the bottom, that's the same as saying, okay, so we could say then that 1 amp then is equal to 1 coulomb per second, or 1 coulomb seconds to the minus 1. I popped this down here earlier on because I am talking almost exclusively about electricity and the conduction of electricity with the charge carriers, which are nearly always in every situation you're going to encounter in this part of the course. The charge carriers are always electrons. However, it would be remiss of me not to mention the fact that, of course, you can have other charge carriers. So in the case of electrolysis, if we have, for example, the electrolysis of copper sulfate, for example, then the copper ions will carry charge to the cathode. So here we've got the copper ions, which are then transferring that charge, and therefore we can have a current in that sense too. Next, we're going to look at point F, the mechanism of conduction in metals as the drift of free electrons. Now, there's not much really to say about that, other than within a metal, there are obviously the ions. For example, in the case of copper, there are many copper ions that make up the structure itself. But then metals, as we know, have lots of free electrons, and the conduction of electricity is the movement of these electrons, the drift, as is sometimes known. Now, what is kind of surprising, I suppose, is when you think about electricity, we tend to think of it being really, really rapid, and it is. When you flick a light switch, a bulb comes on instantaneously. That's something that we've become very accustomed to. What might surprise you, though, is to learn that the speed, or the drift velocity, as we refer to it, of these electrons is very relatively low. It's in the order of 10 to the minus 5 meters per second. So that's an odd conundrum, something to think about. How is it then when I flick a light switch, the electricity can appear, or the current can appear to flow so instantly and rapidly, yet the movement of the electrons themselves is actually very, very slow. Maybe that's a question to pose your physics teacher, I don't know. Okay, I'll look it up, either way. So on to point G then, the derivation and use of the equation I is equal to NAVE for free electrons. Let's get into that now. So in this little diagram here, the blue dots will represent our electrons, and then, you know, within the material itself, we've got all these larger, like, material ions. So these could be like our copper atoms or gold atoms, depending on what we've got. And the electrons then are moving through. Now, to know the current here, we need to know roughly how many electrons we've got in a given volume and the rate at which they're moving. So we're going to just do a little bit of mathematics to try and derive that. Now, the first thing we are going to do is to imagine our wires like a long cylinder, a long, thin cylinder. And we're going to imagine that this length here, okay, that the electrons move through, well, if we think about speed, distance, and time, then distance is equal to, in this case, L, which is equal to speed. So distance is equal to speed times time, or V times T. So the velocity of these electrons in a given amount of time will be the same as, essentially, L. Okay. Now, the next thing then we're going to do is think about volume. Now, let's not get these confused. This is big V for volume, okay? And the volume will be equal to, well, the length times the cross-sectional area. And that's just simple, you know, volume of a cylinder kind of maths, isn't it? All right. And we can substitute what we had in previously then, and we can say that that's equal to V times T times A. So that's our expression for the volume in terms of speed, time, and cross-sectional area. Now, the number of free electrons, because if we want to know current, we have to know how much charge there is, and what how much charge there is, we need to know how many electrons there are. Now, that's going to be given by, I can write that as Vn. Now, what is N? And we need to spend a second just deriving this. This is known as the charge carrier density. And we need to just spend a moment working out what that must mean. It is essentially the number of charge carriers, per unit volume. So as such, it has a unit of meters to the -3 per unit volume. And just to conceptualize what it means, if I had a material like gold, and let's just imagine I had a cubic meter of gold, that would be wonderful. Then I could quit teaching and that would be great. But if I had a cubic meter of gold, within that cubic meter, there would be an enormous number of free electrons. That number, though, would be different, wouldn't it, to a material which wasn't as good a conductor as gold. Gold is one of the best conductors, so it would be higher than that of copper, which in turn would be higher than that of something like steel. So this charge carrier density, telling us the number of electrons per unit volume, also gives us some crude measure of conductivity as well, because the more electrons are available, the more charge can flow, and therefore the higher the current will be. So this charge carrier density is a very important part of this. Now, V times N then, we've already previously defined volume just back there. So V times N we can write as N, of charge carried density, times A times V times T. So that's all from the previous part then. So now we've got essentially Vn, which is the number of free electrons. It's the volume that we've got times the density, or the number per unit volume. Right. Now, obviously, if the volume was 1 meter, then you'd have exactly N, if you like, because N is the number per cubic meter, so you get the gist. Now, the next thing then is to think about the total charge. Now, the total charge is going to be the number of charge carriers, which we've just defined, okay, as NAVT. The total charge Q is going to be equal to N times A times V times T times the charge of an individual charge carrier, which in the case of electricity is E, isn't it? The fundamental charge, E, which we mentioned earlier on. And then finally, recalling that current I is Q over T, so it's the rate of flow of charge. What we can do now is divide both of these sides by T, and we get N times A times V times T times E. And then, of course, if we divide by T, that is going to cancel with that. And I is equal to N, A, V, E. Look, learn it. It could come up. It's possible. The derivation questions, they are, you know, in many cases the difference between A's and B's, all right? Having that depth of knowledge, if you really know your onions and you know the course back to front, you'll learn how to derive an equation like this, because, you know, it's a tough question, and it could come up, all right? So now I think we can tick that off too, and really the conduction of electricity part here is just you know, it's more of a recap of key stage 4, and we're not going to spend too much more time on it because there's not much content to it, and we've gone through the main parts, all right? So we will now jump straight to resistance and start looking at this topic. This one. Right. So first of all, we're going to start off with the definition of potential difference. So we jump to 2.2 now. Definition of potential difference. Before I just get into that, I'm just going to show you this little diagram, because it's a nice little illustration. And the little characters in here representing, you know, essentially the role of voltage, current, and resistance in electricity. Now you can see you've got this guy here at the top, okay? He's sort of, in some ways, trying to restrict or limit the movement of the amps, which of course represent the current. And then you've got voltage then, which is working to drive the current along. And you know what? As a simple explanation for what electricity is all about, that's not too bad at all. I quite like it, okay? And, you know, again, to think about what the quantities of voltage, current, and resistance are, if we compare that to an example of a hose pipe, then the voltage would be like the pressure. So as you turn the tap up, as you turn the tap on, you increase the pressure. The more pressure there is, the greater the flow of water, or the greater the current will be, all right? And then finally, resistance. You've all experienced this, I'm sure. There's a kink in the hose pipe, and that kink in the hose pipe restricts the flow of water, if you like, working against the current. So just as a simple analogy, have that in mind, always very helpful. And now we're going to look at defining potential difference. Now, potential difference is the amount of energy transferred per coulomb of charge. Amount of energy transferred per coulomb charge. And therefore, you can already think about what the unit of measurement is. I know you might know this as voltage, same thing. And of course, it is measured in volts. But from this definition, we can actually, also appreciate that voltage, or 1 volt, is equal to 1 joule of energy transferred per coulomb of charge. So for every coulomb that passes through, say, a power supply, if it's a power supply and it's got a voltage of 1 volt, then that coulomb will receive 1 joule of energy. Right. Okay, so that's potential difference, and I think that, you know what, that will probably suffice as a definition. The idea that potential difference is measured in volts, where 1 volt is 1 joule per coulomb. I think we just covered that. Yeah, 1 joule per coulomb, that's fine. Right, so the characteristics of IV graphs for the filament of a lamp and a metal wire at constant temperature. Okay, let's have a look at that now. So here I have 2 graphs showing the relationship between potential difference or voltage and current, and just so that we remember, this is our voltage and this is our current. Sometimes it's worth remembering that I mean, annoyingly, current is the word current. It has a symbol I and it's measured in amps, which can be confusing, right? But that's why you got to do the work, isn't it? That's why you've got to really crack those books. Anyway, with a resistor, what you'll notice is that these two things are directly proportional. Straight line through the origin is a directly proportional relationship, and essentially any doubling of the voltage will also correspond to a doubling of the current. The ratio of these is constant, okay? And that relationship is given by the resistance. Now, it's worth just noting at this stage what a line like this would mean on the graph. We've got the blue line, we've got the red line. What's the difference? Well, if you look at the red line, for example, if I label this one A and this one B, if you look at A, this could be a different resistor. Which one of these is allowing more current to flow for a given voltage? Which one has the lowest resistance? Now, if you imagine we've got a voltage here, and we draw this across for both, then we can all agree now that resistor A then, for the same voltage, allows more current to flow through. So then this would be a lower resistance, and B is higher. And that's helpful, and that's good to know, especially when we think about and we move on to the filament lamp. Now, in the case of the filament lamp, we haven't got a directly proportional relationship here. And in fact, what you can see here is that the gradient of this line changes. If I was to start off with a small voltage, I might get a significant increase in current to begin with. And then maybe I go to 2 volts, and current's still going up quite a lot. Maybe now I go to 3 volts. What you start to notice is that the amount by which current increases each time is itself decreasing. In other words, the incremental increase in current is kind of going down, and that is because the resistance of this wire, the resistance of the filament in the lamp is getting higher. And we can actually go back to our previous graph so I'll illustrate this. When the line is shallower, then we've got a higher resistance, and when it's steeper, then we've got a lower resistance. So if you look at this line, it starts off quite steep and then it gets more and more shallow as time goes on. So that's implying, of course, that the resistance is in fact increasing, giving it that characteristic shape. The other thing to note as well is that, you know, whether it's positive or negative, this is positive and this is negative, the resistor performs the same either way, and that's also true for a filament lamp. In other words, if you flip it round or you reverse the terminals, then that has no bearing on how that particular component performs. So that is enough to cover the IV characteristics for the lamp and the metal wire. Now, as to why the filament lamp has that shape, we'll get onto that in a moment. So next is Ohm's law and the equation V equals IR and the definition of resistance. Ohm's law, there he is, look, George Ohm, with only one E, strange, isn't it? So when we talk about resistance, we mentioned it already, but it is essentially a measurement of the opposition to current. So, you know, the greater the opposition, the greater the resistance. Now, Ohm's law simply states that current is directly proportional to resistance at constant temp, okay? That bit's important. So for a metal at a constant temperature, we'd expect that the current is directly proportional to the... Oh, no! No. Current is directly proportional to the voltage. I was just testing you. Alright, current is directly proportional to the voltage at constant temperature. In other words, back to the hosepipe analogy, the higher the water pressure, the more current flows. Same here with voltage, right, at constant temperature. Now, we can actually then write this as, you'll have seen it, Ohm's law, R is equal to V over I. You might have seen it as V equals IR, that's fine. But resistance measured in ohms, voltage measured in volts, current measured in amps. Essentially what we're looking at here is the ratio between voltage and current. That's what resistance is. Okay, it's essentially the ratio of those two quantities. And of course you can pop that in a formula triangle, but you guys are probably past that now, being A-level students and all. You don't need formula triangles anymore. So let's see how we've done with that one now, in case we've missed anything off. Ohm's law, the equation V equals IR, and the definition of resistance. I'll say that's done. Okay, we'll give that a little tickaroony. Now, resistance being measured in ohms, where the ohm is a volt per amp. Not much really to say. I mean, we pretty much did that just now, because if R is equal to V over I, and R is measured in ohms, then, you know, because voltage is measured in volts and current is measured in amps, then 1 ohm is equal to 1 volt amp to the minus 1. Okay, that's all that is. The power equations now, the application of P is equal to I times V, I squared R, V squared over R. So let's jump down to electrical power then. We have V is equal to I times R. We have also got electrical power as being I times V. We can combine these two equations to produce other equations, and you should be aware of how that's done. So if I was to, for example, substitute this V value into here, then I could rewrite this one as P is equal to I, and instead of V now I'm going to write down I times R, which is equal to I squared R. So that's one of our equations. And similarly, I can substitute in for I. So if I just rewrite this for a moment, and I say, well, to rearrange this, I could say I is equal to V over R, and then we substitute that in, then I can write another power equation, and instead of writing I now, I'm going to write down, I'm going to write down V over R times V, and that's going to be equal to V squared over R. So essentially, we've got these equations for electrical power. When it comes to past paper questions, it's just a case of choosing the right tool for the job or the right equation for the problem at hand. So I'm actually going to go ahead and say that, you know, those power equations now, you should be able to derive them, you know where they come from. We did all three of those. Part G. Collisions between free electrons and ions gives rise to electrical resistance, and electrical resistance increases with temperature. Right. So I guess this would be, you know, visualizing resistance. And as with the previous topic, conduction of electricity, we imagine our material to contain, I prefer it when it was fuzzy, I don't get it fuzzy. We imagine our material to contain lots of these ions. Alright, so this could be like either, let's just say iron, right? So keep on picking on copper. And then within this material then, we've got all these little electrons dotted about. And as we mentioned before, they have a drift velocity. So when we apply a potential difference across here, then right, our electrons, okay, because they're negatively charged, are going to have a direction of movement, a drift velocity in this direction. Okay? I'm not going to draw them all. But let's imagine, though, this guy here. When that potential difference causes the movement of that electron, and all of these electrons, they can indeed collide with the ions in that material. And it's this collision between electrons and the ions that gives rise to the concept of resistance. It's how we explain, if you like, what resistance is on a particle level. If you were to go for an analogy, sometimes I offer this one, we've mentioned already that you can think of, you know, electrical current like the water flowing in a river. Were we to throw loads of rocks in that river such that it opposed the flow of water significantly, then we would reduce the overall rate of flow of that water and the current. And you can think of it as analogous to that, really. So the more collisions we have between the electrons and the material ions, then the greater the resistance will be. Now, here's where the temperature part comes in, though, because when my electron, okay, you know, it collides with the ion, then it's going to impart some of its kinetic energy. Now, these ions will then gain that energy, so energy is transferred. And when energy is transferred, it will cause them to vibrate. Okay? And that vibration will cause them to, you know, oscillate and move about. Now, here's where we can explain why the resistance increases. Because If now, after a certain amount of collisions, the material ions are vibrating and moving about, then the probability of further collisions will in fact increase. If the probability of further collisions increase, then that will mean that we'll have in turn more resistance. It's a bit of a feedback loop, really. It's a bit like, imagine in people running down a wide corridor, and there are other people standing in the way, like really big people, like, I don't know, sumo wrestlers or something like that. And then those people are jumping back and forth. If they're jumping back and forth and sort of vibrating on the spot, then they're more likely to collide with the other people running down the corridor, which in this analogy are electrons, and therefore fewer electrons will get through, or there'll be more collisions. That is resistance in a nutshell, on a particle level, I suppose. Now, with all this in mind, it's worth then popping back to our filament lamp, because we can use this to explain what's going on here. As we increase the potential difference in more current flows, we get more collisions between electrons and the material ions, and therefore the temperature of the metallic conductor will start to increase as those atoms start to vibrate. As the atoms start to vibrate more, that in turn causes more collisions. If you like, the likelihood of electrons passing through unimpeded goes down, and there are more collisions. And when we have more collisions, we have a greater opposition to the flow of charge, and therefore greater resistance. Again, potentially, you can imagine that being sort of a 6 marker, couldn't you? So I'm going to give that one a little tick now. The application of R is equal to rho L over A, the equation for resistivity, this little keyword here. Resistivity, where have I got that down? Okay, so resistivity then. When we think about resistance, especially in the context that we just did, if we're imagining the things that are going to impede electrons, or if you like, imagine what would make it more likely for an electron to undergo a collision. We've mentioned temperature being one of them. But another one is just simply the dimensions of the material itself. So if I've got a really long wire, and I've got my electron starting at one end, and I've got quite a lot of ions, then the chance that the electron is going to get through from one end to the other is going to be lower if the wire is even longer. If it's only got, like, so many to get through, it might well zip straight on by without bumping into anything. But the longer that wire is, the longer that corridor is, the more chance it's going to have of having a collision, and therefore the greater the resistance will be. So the resistance of a given material is proportional to its length, L, all right, in this case, L. The resistance as well is also proportional, or if I like, inversely proportional to the cross-sectional area. In other words, in this first analogy, I did a very narrow wire. What if I had a really thick wire? Well, if I had a really thick wire, the electrons are not so, if you imagine it in simple terms, bunched in. They're not walking in single file. They've got plenty of room, and therefore they'll flow that much better. So the larger I better draw this as a circle, isn't it? The larger the cross-sectional area, the lower the resistance will be. That's why R is inversely proportional to A. All right. In other words, the larger the area, cross-sectional area, the lower resistance will be. And then finally, resistance is also directly proportional to this concept known as resistivity. Now, resistivity is simply a measurement of a given material's resistance, how kind of resistive it is. And that is an innate property of that material. And it's got a symbol rho, which I haven't done brilliantly, but it's not bad. It's as good as my lambda from the other day. I mean, that was quite an event, I think you'll agree. But yeah, resistance then is proportional to this concept of resistivity, and it's an innate property of that material. So we can put all that together into an equation, and it comes out as R is equal to rho times L all over A. And that is our resistivity equation. And the resistivity varies from material to material. And yeah, you want a low resistivity if you want something to be very conductive. But then conversely, the opposite for something which you want to have quite a high resistance. A good example of this is, in fact, the filament in a light bulb again. The filament in a light bulb is actually made, or it was, they're not so common now, but made out of tungsten. Now, tungsten has quite a high resistivity, which is appropriate because in the case of a light bulb, let me draw it, you had this kind of thing going on. Now you'd use, first of all, you'd use a material with a very, very high resistivity. This wire was also very, very long, so inside a light bulb, if you unravel it, that wire, you'll see that wire is actually coiled and coiled again, coiled on itself. It's a very long wire, so you increase the resistance then by having a very long wire, and it's inversely, so it's very thin wire also. So also it's a very thin wire, which also increases the resistance. So in other words, the filament in a light bulb is specifically designed to have a high resistance by making it out of a material which isn't particularly conductive. It's a high resistivity, making it very long and having a very low cross-sectional area, making that wire very thin. Why have a material to have such a high resistance? Well, I'm glad you asked, because if it's got a high resistance, that's going to mean a lot of collisions between electrons and the ions within that material. Lots of collisions mean that the electrons are passing on a lot of energy, and that's going to cause the ions to vibrate. And that vibration manifests itself as an increase in temperature, so the temperature goes up. You get more collisions because of the vibrations, the temperature goes up again. And of course, when things get very hot, they start to glow. And that's exactly what you want a light bulb to do. So you are engineering, using this equation, a situation where you will create a high resistance and therefore an increase in temperature, which ultimately will cause that object to glow, which is exactly what you want to get out of a light bulb. There's a little example there, which you can try. So if you want to pause the video and give it a go yourself, by all means do so. I haven't got time to go through that now, but just remember, watch out for your units of measurement, okay? They're all over the place here. Work in meters, stay safe, people, stay safe. So I'm going to say that that is pretty much done. I'm not going to go through the practical for determining resistivity. I think practicals, specifically the specified practicals, would probably be worthy of just doing in its own video at a later date. The idea that the resistance of metals varies almost linearly with temperature over a wide range. Let's take a little look at that. Yeah? So this experiment you may or may not have done, and it's, as it says on the tin, it's an experiment which investigates the relationship between resistance and temperature, and you wrap a length of wire around a frame making sure that the wire doesn't touch itself, because obviously you can sort of, I guess, short it or reduce the length of it. You want a fair length of that wire in there, so you've got significant resistance. And then you vary the temperature by adding a heat source. Could be Bunsen burner. I've seen this done in a kettle. I did it myself in a kettle once, rather unsuccessfully. But there's variations on this. I'm sure you've done something similar in school yourself. Now, when you increase the temperature, you see a corresponding increase in resistance. And we've covered that. But of course, that will also cause a decrease in resistance for a decrease in temperature. This is where things start to get interesting. Now, I don't think there's much to say about this other than this relationship is linear, i.e. for a given increase in temperature will cause a corresponding linear increase in the resistance. Point J then, the idea that ordinarily collisions between free electrons and ions in metals increase the random vibration energy of the ions, so the temperature of the metal increases. I'm going to say we've done that. We've talked about that. Or sorry, I've talked about that at length. What is meant by superconductivity and superconducting transition temperature? Ooh, that sounds interesting. Well, superconductivity then was something discovered in 1911, all right? And essentially, it's about walking the temperature backwards rather than forwards and cooling things down. And as we cooled conductors down and metals down, and we saw this reduction in resistance, something very surprising happened when we got down to, if you like, close to absolute zero. Now, I'm assuming here we are okay with the concept of absolute zero and its relation to degrees Celsius. Degrees Celsius in the sense that Celsius scale is defined really by its starting point, which is the freezing point of water, and by the boiling point of water, and then you divide that up into 100 divisions, and you call 0 and 100 on that scale. But of course, we understand that temperature goes far lower than 0 degrees, and the Kelvin scale is linked to the idea that there is an absolute limit to how cold things can get. It's quite a great discovery when you think about it. Is there a limit to how hot stuff can get? Well, I suppose, yeah. I mean, ultimately, it's governed by how fast particles can move, and as we know, I mean, the universe does have a speed limit. But that's like millions and millions and millions of degrees. The limit for how cold something can get is pretty far more accessible, and it's minus 273 degrees Celsius, which we then call 0 degrees Kelvin. I'm not going to go into exactly why there is an absolute limit for how cold things can get, and why we can't go any lower than that. We'll save that for another time. But as the temperature started to decrease and the resistance also started to decrease, something quite magical happened at what we call now the transition temperature. And that was that the resistance of, in this case, mercury, I think it is, yeah, of the mercury wire went to 0. So 4.2 degrees Kelvin. It actually went from having a value to nothing. And this term then was referred to as superconductivity, or its phenomena, I should say, was referred to as superconductivity. Now, I can't even say his name. Camerlinghomes proposed in 1913 a 10 Tesla solenoid. Now, Tesla for another time, but that's basically how the strength of the magnetic field, and it is basically implying that you could use this principle of superconductivity to produce enormous currents and therefore epically strong electromagnets. And I mean, just to take it one step further, we have since, of course, discovered that there are many, many metals and mixtures of metals that will produce this phenomena of superconductivity. And it's at the moment one of the hottest areas, ironically, one of the hottest areas in physics, even though it's about being really cold. It's all about trying to produce a superconductive material which has the highest transition temperature. Now, if you look back with the old mercury, it's 4.2 degrees Kelvin, and it's just above absolute zero. The only way you can achieve that temperature is using something like liquid helium. Now, liquid helium is a bit of an issue. There's not a great deal of supply. And one day we could face a situation where there is a massive liquid helium shortage, which will not only have big implications for superconductivity, because we won't be able to achieve superconductivity because there's not enough helium, but also, of course, children's parties and balloons will be forever changed. If we can, though, produce materials, which have a higher superconductive range, if we can produce a critical transition temperature up towards this value here, liquid nitrogen, and we can use liquid nitrogen to create superconductivity in a material, then that's going to have huge, far-reaching implications for society and technology as a whole. There's a big race on at the moment to produce something which is a superconducting material higher than 78 degrees so that we can use liquid nitrogen to produce that temperature and therefore get all the benefits of superconductivity. What are they, Mr. Ridd? I hear you say. Well, I mean, here's a couple. First of all, you use superconductivity to produce enormous currents in wires because there's no resistance effectively. And if you produce enormous currents in wires, you can produce epically strong magnets, which is what is going on in the LHC. And if you didn't know what the LHC was, it's the Large Hadron Collider. This is the device, the machine that they use to smash particles together close to the speed of light. It's where the cutting edge of particle research is today. So one of the applications is you can use superconductivity magnets and therefore particle accelerators. Sorry. This is kind of cool. Maybe one day we'll have, maglev trains, so trains with like virtually no resistance or no friction because they are levitating effortlessly above. Would it still be a rail? I don't know. But the train would be levitated using really strong magnetic fields produced by superconducting magnets. And then finally, MRI machines is another application. There are also military applications as well. But in addition to that, and probably more significantly, if one day in the future, who knows how far it'll be off, our parts of our electricity network, parts of our national grid are, if you like, transferring electricity with zero resistance, then that's going to mean huge efficiency gains, which will ultimately mean that the amount of energy we have to produce at source is a lot less, because less energy is lost in transition, which would be great for the future also. So let's see how far we got. The fact that most metals show superconductivity and have transition temperatures of a few degrees above absolute zero. Yeah. Certain materials, high temperature superconductors, having transition temperatures above the boiling point of nitrogen. I mentioned why that's important, because nitrogen is abundant and that's a really big deal. So the race is on for that. Who knows? Maybe one of you guys will go and make that material, and then you can say, oh yeah, maybe you can mention me. I don't know. Some uses of superconductivity, for example, MRI scanners and particle accelerators. I think we've covered that. Okay, so I think we're going to leave it there. So that is an overview then of the conduction of electricity, and of course and resistance, I should say. My name is Mr. Ridd. Don't forget to check out the Car and Camera website for this video and a whole bunch more to help you with your revision for those all important exams. Thank you for listening.